So we've got a big chapter on linear algebra to do. And then we're going to change gears and we'll be looking at solutions of nonlinear equations and optimization in general. So we're going to take our linear algebra skills in the latter part of Rob 101. We're going to wade into the world of nonlinear equations and how to optimize nonlinear functions. Okay, so there's some really cool stuff coming up. But before we get there, there's some tools in the linear algebra toolbox that we need to go through. And so this chapter is called RN Take 2. So the big takeaways we're going to have are there special subsets in vector spaces that are closed under linear combinations. And we give those things a name. They're called a subspace. Okay, so subset is any collection of points from it, but if it has extra properties, we call those subspaces. So these are in the what you're going to learn part at the beginning of the chapter. I would just leave a space in your notes of about a page, and you can fill these in. There'll be two very special subspaces that we define. One is called the range of a matrix, and the other one is the null space of a matrix. And when you understand these two subspaces, you know everything that can possibly be known about the solutions of a set of linear equations. So it's a way to parameterize all possible solutions and all of the non-uniqueness, et cetera. It's all captured in these two geometric objects. So that's just awesomely cool, okay? Now the thing is, these objects will either have only one element in them, or they'll have an infinite number of elements in them, you know? Remember lecture 1, we were going about solutions of linear equations? And we could have a unique answer, we could have no answer at all, we could have an infinite number of answers. There was no linear equation that had precisely two distinct solutions and not an infinity of solutions. So this will be the structure of that will show up in these subspaces. So in general, these subspaces are going to have an infinite number of elements in it, and then we're going to figure out how to generate them with a finite set of vectors. So that's what's going to be really awesome about the notion of a basis. You take this set, which is infinite in number, and you can generate it by just doing linear combinations of a few vectors. That will be called a basis. There's going to be these really special types of bases where the vectors form right angles one to another. Okay, so we're going to understand what does a right angle mean in Rn. And that's going to lead us to maybe the world's second most favorite matrix factorization of all, which is called the QR factorization. We started with maybe the world's third most favorite matrix factorization, the LU factorization, and we started with that because it's the most approachable of the favorite and useful and highly powerful matrix factorizations. But this one will be a decomposition of the matrix into a matrix that's orthogonal. And orthogonal matrices, super cool. You want to invert it, you just transpose it, okay? There's nothing more beautiful than being able to compute a inverse by doing a transpose. So one of the questions that people were asking, you know, in the what did you learn in chapter 6 and stuff like that was, why would you ever want to do the transpose of a matrix? Well, here I'm showing you now. It's that you can actually, we will eventually be able to calculate the inverses of certain matrix by just transposing them. And then we'll have the other part of the matrix factorization is upper triangular, just like when we did LU. And you guys know how to solve equations when you've got the LU, the upper triangular part. And then the only better matrix factorization is called the singular value decomposition. It's in the appendix of our book. So if a year from now you're feeling like, okay, I'm ready to start attacking that one, it's all developed in the appendix, okay? Okay, so that's what's to come, and I'm not sure how many lectures it will take us to get through it, because I want to do it carefully and make sure that we understand the concepts. It's a little abstract, but the power you get out of this abstraction is really, really useful to engineers, physicists, applied mathematicians, all of them. Okay, so we're working in Rn, so let's just recall the two fundamental properties about Rn. So Rn, we identify with column vectors, and then since all of them are column vectors, we drop the word column and we just call them vectors. We could have identified Rn with row vectors, and then we would have dropped the word row and only worked with list of numbers written in a row, and then we would have called those vectors. In different circumstances, you use different representations of Rn. In Rob 101, for us, Rn is always a vector with n components, arranged as a column. And then we defined how to add two vectors by just adding up the individual components. We called that vector addition. And we defined how to multiply a vector times a scalar. So a scalar is just a real number. It's just another term for a real number. We took a scalar times a vector by multiplying each component of the vector by the scalar, and that's called scalar times vector multiplication. Those are the two fundamental ingredients of defining something called a vector space, the space of all vectors, and that's what Rn is, the space of all vectors with n components. And then this is a simple result that I'll give you time to write down because it's going to be crucial to what we're doing, is that 1 and 2 hold, so I can take a set and look at it's closed under vector addition. 2, it's closed under multiplying vectors by scalars, or I can just take all linear combinations in Rn, and I still get a vector in Rn. So linear combinations, they're just, if I take alpha equals 1, beta equals 1, I'm doing vector addition. And if I take beta equals 0, I'm doing scalar times vector multiplication. So it's just, this is linear combination. It's just combining the two elementary operations of vector addition and scalar times vector multiplication. So you can check those properties one at a time, or you can just check using the more general notion of linear combination. Okay, so that's what's going on there. And Rn, you can define it either way. You can define it as columns and then things, and you can define the vector addition and scalar times vector multiplication separately, or you could go straight to the notion of a linear combination, and then you could say all the vectors in Rn satisfy that. Completely equivalent. Okay. How we doing? Pretty harsh warm-up for a Monday? Woo, yeah, okay. Let's get down to brass tacks then. Okay, so let's just recall some notation. I think it's been a really hot thing to be teaching set theory type stuff in high schools these days. So what does it mean that that V is a subset of W? Okay. So V is contained in W, is a subset of W, if and only if V an element of V always implies that V is an element of W as well. Okay, so that's the definition. That's what V subset W means. Every element of V is also an element of W. Now, where the notation sometimes varies in different books and different instructors is this. Whoops. We allow V equals W, okay? In other words, any set is a subset of itself. Okay, so V contained in W is fine. W is contained in itself, so we can write W is contained in W. So there's no problem with that. With some books, you know, you put a little slash here to say V is strictly smaller than W. There's at least one element of W that's not in V. We don't do that, okay? So that's just all I'm trying is get that notation. And if you've never had to deal with that notation, I'm proud of the instructors that you've had. Okay, so subsets. Definition. So let V be a subset of Rn. Okay, and I'll write it out initially just to make sure, you know, when I write V, that subset symbol Rn, the be a subset is redundant, but sometimes the Department of Redundancy department is useful, okay? Just when you're first learning something. Okay, definition, let this be a subset. V is a subspace of Rn. Let me get my R a little bit better, and that'll give you time to catch up on your writing. Subspace of Rn. If V is closed under linear combinations. Ooh. Okay, you get that? And we'll elaborate on what does it mean that a set is closed under a type of operation. Okay. That is for all pairs of scalars, alpha 1, alpha 2 in the reals, and vectors v1, v2, an element of V, the linear combination alpha 1 times v1 plus alpha 2 times v2, that is also an element of V. Okay, so being closed under an operation, I take the set, I manipulate the elements in the set with a particular operation. Our favorite operation is taking linear combinations now. And whenever I take those linear combinations, I don't leave the set. It's still an element of the set. So it's closed under that operation. Okay, so that's pretty sophisticated vocabulary that is typically used in more advanced math courses. But I think this just kind of helps us understand the structure of these sets. Now, when you're checking that something is a subspace, you can do it two different ways. You can check it's closed under linear combinations. Okay, that's the definition. Any linear combination of elements of V is also an element of V. Or you can break that linear combination down into the elementary things of doing vector addition and scalar times vector multiplication. So it's up to you. It's completely equivalent. V is closed under vector addition and scalar times vector multiplication. It's your choice. Completely equivalent. Which one do I use? Both, okay? It's a trick question. Depends on the setting, okay? And especially if I'm trying to show something is not a subspace, I just got to find one of those properties that fails, and I just use it, okay? So if I'm studying a problem and I'm seeing if I can get it set up, whether it's a subspace or not, I'll check one of these more elementary things. I'll check this one or I'll check this one. If I've got a really good hint that it probably is, I might just go directly for this and then I'm done in one step. So it's a question of experience and taste. So for you, because you have a choice, it's like, I don't know which one to apply. Well, choose one and just go for it, okay? That's what I would suggest. This is cool. Here's an elementary screening test. To always apply first. If V contained in Rn is a subspace, then the zero vector, and I'm going to emphasize it's the zero vector in Rn, is an element of V. Yeah, first thing you do, if the zero vector is not in it, it's not a subspace. And why is that true, okay? Why is that? Why? Well, suppose V is not empty. So suppose there's some vector in V. Then the zero scalar, okay, times V is an element of V if V is a subspace. That's just one of the possible numbers in the reals that you could multiply V by and still get something in there. And 0, 1 by 1 times V is equal to the n0, n by 1 vector, okay? So that's the first thing you check. Now, why is that interesting? Well, I don't know. Maybe you won't find this interesting, but I'm going to hope you do. Here's R2, just because I can't draw R3 very well. So this is like X1, and this is like X2. And if you want to call them X and Y, I'm not opposed. Okay. Here's a line. Here's a line. Here's a line. And let me label them L1, L2, L3. Now, which of the lines L1, L2, L3 is potentially a subspace? You know, can we eliminate some of them just by our very simple screening test, okay? So, does L3 contain the 0 vector? The answer is no. Does L2 contain the 0 vector? The answer is no. And I worked really hard to make sure that L1 contained the 0 vector. And for me, that was almost a superhuman effort to get it to go through there. Okay, so only, what number was it? L1, okay? So only L1 is potentially a subspace. It actually is, but we're not going to check it now. So here's a really good quiz question over this. All lines in R2 define subspaces. The answer is false, okay? In fact, only lines that pass through the origin define subspaces. So the intercept has to be 0, okay? Any slope is allowed, so there's an infinite number of them, but there's only ones with 0 y-intercept. Okay. How are we doing so far? We know the simplest screening test, and that's a lot easier than taking points on L3, 2 points, and doing a linear combination and getting something else, okay? So that makes that a lot easier to do. Okay, so now we're going to do a little more abstraction. Okay. We can view n by m matrices as functions. Ooh. Okay. So A is going to have n rows and m columns. I'm going to define a function that takes elements in Rm and maps them to elements of Rn by and I'll let you guess what I'm going to put on the right-hand side there. Okay, so I can multiply A by an m by 1 vector. Okay, so x here, this means I'm taking m by 1 vectors and producing n by 1 vectors. That's all that notation means. Now, there could be sines, cosines, and crazy things in there, but I'm not going to put anything crazy in there. I'm just going to define that to be A times x. Okay, so x is m by 1, A is n by m, and so this is an element of Rn. So it all works. It's a function from, we would call this the domain. You may have learned that this is called the range, but it should be called the codomain, okay? Because we're going to use the word range for something else. Okay. So the following subsets are naturally motivated by the function view of a matrix. Okay, so for anyone who's really worried and they're getting a little upset by the level of abstraction, I can promise you by Wednesday we'll be back down to earth, okay? So you gotta live with it for Monday and maybe part of Wednesday. And then when we get to the orthogonal vectors, you're just gonna have so much fun when we get there. Okay, so the definition, part A, null of A okay, it's going to be set of all vectors in Rm such that when I apply A to them, I get the 0 vector in n by 1. Whoops, didn't hit hard enough. Let you catch up. You see, I'm viewing A as a function that takes vectors in Rm and produces vectors in Rn. And now I'm looking at all of the vectors here that under this function get mapped into the 0 vector. Okay, I'm going to relate it to solutions of linear equations in just a second and why we really care about this. Whoops, I should give the name of that, okay? This is called the null space of A. Okay, so the null space of a matrix is the set of all vectors that get mapped into the 0 vector. And then R of A, do this one in blue for some reason. This is all the points in Rn such that y equals ax for some x in Rm. And this is called the range of the matrix. Okay, so if I had a function, I can look at all of the points that get mapped into 0, that's the null space. And then I can apply this function to every single vector in Rm, and then it may be true that I can land on every single vector in Rn, or it may not be true. Maybe I only hit a smaller set of vectors. So that set of vectors is called the range of the matrix. For example, suppose the matrix is the 0 matrix. Rectangular, all zeros. What is the range? Just the 0 vector. It's not very big, okay? It's not very big at all. If m and n are equal, and A is the identity matrix, then I can hit every single vector in the range, okay? So the size of the range is going to be really important. We will eventually call that the dimension of the range and the dimension of the null space. Okay, so range of A, it's everything I can hit in Rn by choosing some vector x in Rm. And those vectors have to be related by y equals ax. That's the range. Okay, so that's why we don't call this the range, because if this is the trivial function that maps everything to 0, the range is not Rn. That's why we want to call that the codomain of the function. Domain of the function, codomain. That question will never be on any quiz or anything. It's just for your own edification. Okay, so we got this abstraction. Is it useful to us? Relation to AX equals B, system of linear equations, right? That seems very concrete to us now. Somewhere around the end of the first week, that was still seeming very dubious when we wrote down AX equals B. It was this mind-blowing set of symbols, but not anymore. AX equals B, that's about as concrete as we can get, and we're very happy with that level of abstraction. Okay, so let's relate these two sets to solutions of AX equals B. Okay, so let's suppose that X bar is a solution of AX equals B. Okay? Conclusion, AX bar equals B. That's the only thing that being a solution means, right? Now, let's suppose, and I'll call it X tilde. Suppose it's in the null space of A. And look at this. What happens when I apply A to the vector sum of X bar and X tilde? Well, A applied to the sum of the vectors is the sum of A applied to the individual vectors. Oops, there's a bar missing. We know this is B because it's a solution. And we know this is 0 because it's in the null space of A. That means A times x tilde is 0. So this equals AX bar equals B. And this is the 0 n by 1 vector, okay? So the conclusion is once you know one solution to AX equals B, you can generate all solutions to AX equals B once you have computed the null space of A. Okay, so null space of A lets you understand the set of all solutions to the equation AX equals B. If the null space only has the 0 vector in it, then you have uniqueness if you have a solution, okay? Now this is going to be towards the very end of the chapter, but I mean, if all of these things are solutions, how might you choose one of them? Question?
I got a question. So I thought, like, for a system of equations or whatever, wasn't there only one solution? So how can you generate all solutions if there's only one solution?
Okay, so yeah. One solution. For example, let's take A is 0, 0, 0, 0, 0, 0 times x1, x2, x3 equals 0, 0, right? This is 2 by 3, 3 by 1, 2 by 1. So everything is a solution to this, right? Yeah, so the null space would be all of R3 in this case. So when we have AX equals B, we certainly don't have uniqueness of solutions in general. It's only when if it's rectangular, the determinant of the matrix should be non-zero to get uniqueness. So we often have multiple solutions to an equation. And if we have 2, we have an infinity. That's what we're going to see really soon. So going back, if all of these things are solutions, one way to choose them is to choose the solution with the smallest possible length. It's a similar problem to when we had AX minus B has no solution, which we got lots of problems like that when we did regression fitting functions to data. We would find the solution that minimized the error in AX minus B. And so here, this is what people call a dual problem. It's very similar to it, okay? If you understand one problem, you kind of understand the other. Is that once you know this, you're going to optimize over all of these vectors to find the solution of minimum norm. And that turns out to be a really powerful idea in engineering. So understanding this set tells you about non-uniqueness of solutions to your system of equation. Okay, now so that's the null space. Now, what about the range? Okay, so what is that telling you? Well, so R of A, let me write down the definition again. Set of all y in Rn such that y equals ax for some x in Rm, because A is n by m. Now, I'm calling vectors in Rn y. But, you know, we often call them b. Everybody agree that we often like b to be on one of the symbols that we use? Okay, it's kind of unfortunate, but you know, notation is everything. And sometimes you just need to change it a little bit, and then your mindset of how you look at an equation is completely different, okay? It just changes how you look at the equation. So I'm just going to note, you know, I can call my vectors in Rn anything I want, okay? So I'm going to call it B. So when I do that, the range of A equals the set of all B once again in Rn. Now I'm just going to write Ax equals B. And I want this equation has a solution. Okay. B equals Ax for some x is the same thing as saying Ax equals B has a solution. It's exactly the same statement, but now I see what the range of A is. The range of A is equal to, well, I guess I've already said that. What I want to say is something different, sorry. Your notes aren't as powerfully erasable as mine. So range of A is the set of all vectors B and Rn such that Ax equals B has a solution. And another way that we can write that is, oh my gosh, now I'm falling apart. Ax equals B has a solution if and only if B is an element of the range of A. So it's another way of thinking about the range of A. So once we calculate the range of A, the set of all points that we can map onto in Rn by varying x, that tells us about solvability of our equation. Okay, so here's the big deal about these sets. Claim null of A, let me do these separately, sorry, is a subspace of Rm, and range of A is a subspace of Rn. Whew. Okay. I'll use the Rob 101 symbol for proof, Y, okay? So it really means proof, right? But we don't do proofs in Rob 101, right? So, but we can give explanations, so that's all I'm doing, okay? So Y is the null space, a subspace, and Y is the range. So we'll give the reasoning for the null space. The range is a little bit more complex, but it's the same type of thing, okay? So explanation. Not the range for the null. Okay, and actually what I'll do is I'll put both of these in the book eventually. This way of approaching the material is not how I have the book organized, but it will be soon. Okay, so we want to show the null space is closed under linear combinations, okay? So if you're going to do a proof, an explanation, always write down what you're trying to show. See, we want to show the null of A is closed under linear combinations. Okay, so how do we generate linear combinations? We'll take X and X bar to be two vectors in Rm. And we'll let alpha and alpha bar be two scalars in R. And we don't want them in Rm, we want them in null of A, so I apologize. You got to take them in the null space and then take a linear combination of those. They would be in Rm, but we want them to be in the smaller set, null. So we just take A and we form the linear combination. And we just need to see that we get the zero vector. Well, that's A times alpha X plus A times alpha bar X bar. Because a matrix applied to a sum of two vectors is the sum of the matrix applied to the two vectors. And then that scalar can come out in front. That's alpha A times X, then alpha A times X bar. This is alpha times the zero vector in Rn. Plus alpha bar, once again, times the zero vector in n by 1. And so that's just the zero vector in our n by 1. Okay, I write this and then we're done. And that's simply because by definition, A times X equals 0 if and only if X is in null of A And A times X bar equals 0 is the definition of X bar in null of A. Okay, and then that means alpha X plus alpha bar X bar is an element of null of A because A applied to them is 0. So that's it. So these special sets are really important for describing all of the possible ways our equation can have solutions and not have solutions.